Epoxies are one of the most important classes of polymers due to their unique attributes for modern materials. By definition, epoxies must contain at least two epoxide groups per molecule, as they require cross-linking for their various applications. An epoxide group is a cyclic three-membered strained oxirane ring that is highly reactive, especially in the presence of active protons. The term epoxy is derived from epi, a Greek prefix meaning on or near, and oxy, the combining form of oxygen. Thus, epoxies have combined oxygen atoms in the form of an epoxide ring. The most widely used epoxies are glycidyl ether epoxies, which are made by condensing reactive hydroxyl-containing compounds, mainly aromatic diols, with epichlorohydrin. However, non-glycidyl epoxies are also available commercially, although they are not used solely to generate epoxy thermosets. Non-glycidyl epoxies, along with monofunctional epoxies, are mostly used as reactive diluents, viscosity modifiers, and adhesion promoters. Bisphenol glycidyl ether epoxies are cross-linked by reaction with curing agents to transform viscous liquid or semi-solid products into solid, rigid, insoluble, and intractable thermosets. The synthesis of the first epoxy from epichlorohydrin appeared in 1927 in the United States, although Lindman of Germany made the first attempt to synthesize it by reacting hydroquinone and epichlorohydrin in 1891. The first successful syntheses of a bisphenol A, BPA-based epoxy were reported in 1936 by Pierre Caston of Switzerland and Sylvain Greenlee of the United States. Furthermore, the commercial production of epoxy began in 1947, based on the research of Caston, as licensed by Ciba Limited of Switzerland. In the 1960s, orthocresol and formaldehyde-based epoxies were produced, and in 1965, Ciba actively started producing epoxy resins. Types of epoxies. Industrial epoxies are available in two main types: glycidyl ether epoxies and non-glycidyl epoxies. Although epoxies can be classified in a variety of ways depending on their characteristics, based on their raw materials, they fall into three categories. Depending on the use of bio-based content, they are categorized as petroleum-based, zero bio-based content, epoxies, fully bio-based epoxies, and partially bio-based epoxies. Similarly, based on molecular weight and viscosity, there are three types: low molecular weight liquid epoxies, medium molecular weight semi-solid epoxies, and high molecular weight solid epoxy materials. Depending on functionality, epoxies are classified as either low functionality, with 2 or 3 epoxy groups per molecule, or high functionality, with more than 3 epoxy groups per molecule. Similar to other polymers, these epoxies are also classified as conventional linear epoxies and dendritic or hyperbranched epoxies, depending on their structural architecture. Dendritic, tree-like growth and appearance, or hyperbranched epoxies have highly branched molecular structures, with large numbers of epoxy functionalities and much lower viscosities, higher reactivities, and better solubilities and compatibility with other epoxies than the linear analogues of equivalent molecular weight. Biodegradability is one of the most important requirements in contemporary research. Based on the degree of biodegradability, epoxies are classified as fully or completely biodegradable, partially biodegradable, and non-biodegradable. Epoxies can also be classified as synthetic when they are generated in a laboratory, for example, glycidyl ether epoxy of the bisphenol type. Semi-synthetic when epoxy groups are introduced into natural compounds, for example, epoxidized natural rubber or epoxidized vegetable oils, or natural when they are directly obtained from nature, for example, Vernonia gallamensis oil. V. galamensis is an oilseed crop found in arid and semi-arid zones, whose seeds contain about 40% oil. This oil is composed of triglycerides with 70 to 80% of the epoxy-containing vernolic acid. Furthermore, these natural epoxidized plant oils, namely V. galamensis and Stoichiometric laevis, are of significant interest to researchers, but their low epoxy values limit their actual applications as individual epoxies. Synthesis of epoxies. Epoxies require appropriate organic compounds, including aliphatic and cycloaliphatic compounds, aromatic dye and polyols, and epoxides. The most widely used epoxies in commercial products are manufactured as glycidyl ether derivatives of the bisphenol type, where BPA-based epoxies comprise more than 75% of the total volume, and are available in a wide range of molecular weights. These glycidyl ether epoxies are generally produced by the direct polycondensation reaction of aromatic, and aliphatic, or only aliphatic, dye and polyols with epichlorohydrin. Catalysts. Many basic catalysts have been used in the preparation of glycidyl ether epoxies to facilitate the removal of HCl from the polycondensation reaction. These include sodium hydroxide, potassium hydroxide, calcium hydroxide, lithium hydroxide, sodium carbonate, calcium carbonate, potassium carbonate, sodium bicarbonate, potassium bicarbonate, calcium bicarbonate, and lithium bicarbonate, although NaOH is the most commonly used. Glycidyl ether epoxies are generally prepared by either the original taffy process or the fusion process. In the taffy process, BPA reacts with epichlorohydrin in the presence of a stoichiometric amount of a base such as NaOH. The molecular weight of the resulting epoxy is controlled by manipulating the molar ratio of epichlorohydrin to BPA. In this process, the use of an excess of epichlorohydrin and about 30% aqueous NaOH results in a reaction mixture in which the organic phase contains the epoxy and epichlorohydrin, whereas the aqueous phase contains the NaCl salt. Initially, the organic phase contains BPA and epichlorohydrin. However, as the reaction proceeds, the organic phase becomes increasingly viscous with the formation of epoxy, and the mixture becomes taffy-like. In practice, the taffy method is used to obtain low molecular weight epoxies with maximum epoxy equivalent weights of approximately 1,000 grams per equivalent. The base catalyst helps to open the epoxide ring through the nucleophilic attraction of the phenolic hydroxyl group on the primary carbon atom of epichlorohydrin in the initial stage of the reaction. However, the epoxy is formed after dehydrochlorination with the generation of an oxirane ring. The purified epoxy is obtained by separating the aqueous phase and the unreacted epichlorohydrin using vacuum distillation under reduced pressure. However, the use of co-solvents and the azeotropic removal of water increases the yield and minimizes the formation of insoluble polymer. Chloride content is one of the problems with this method. For some applications, especially in electronics, low chloride content epoxies are preferable. Non-glycidyl epoxies. In contrast to glycidyl ether epoxies, a non-glycidyl epoxy, such as an epoxidized unsaturated vegetable oil, is generally obtained by the in situ peroxidation of double bonds using organic or inorganic peroxides or halohydrins and molecular oxygen. Peracid method. Non-glycidyl epoxies have been prepared routinely using the Peracid method. Generally, the epoxidation of double bond-containing compounds or polymers, such as vegetable oils, natural rubber, and other bio-based compounds with unsaturation, can be performed by 4 different routes. 1. Epoxidation with percarboxylic acids catalyzed by acids or enzymes. 2. epoxidation with organic and inorganic peroxides catalyzed by a transition metal. 3. Epoxidation with halohydrins such as hypohalous acids, HOX, and their salts. And 4. Epoxidation with molecular oxygen. Among these methods, the oxidation of the double bond using organic peracids is the most industrially accepted approach. In this process, a number of organic acids can be used. The Peracid reaction, or Peracid epoxidation, is the chemical reaction of an alkene with a peroxy acid to form epoxides. It is named after Nikolai Peracid, who first reported this reaction in 1909. A widely used peroxy acid for this reaction is metachloroperoxybenzoic acid, MCPBA, due to its stability and good solubility in most organic solvents. The reaction proceeds through what is commonly known as the butterfly mechanism, wherein the peracid is intramolecularly hydrogen bonded at the transition state. Although there are frontier orbital interactions in both directions, the peracid is generally viewed as the electrophile and the alkene as the nucleophile. In support of this notion, more electron-rich alkenes undergo epoxidation at a faster rate. He reaction mechanism is believed to be concerted, with a synchronous transition state. A number of things need to be accomplished. In addition to the oxygen donation, the leaving group must leave, and a proton must be transferred. Chiral epoxides. Chiral epoxides are produced by epoxidation of prochiral alkenes. When the catalyst is chiral, or the alkene is chiral, then asymmetric epoxidation becomes possible. Prominent methodologies are the Sharpless epoxidation and the Jacobsen epoxidation. The Sharpless epoxidation allows the enantioselective epoxidation of prochiral allylic alcohols. The asymmetric induction is achieved by adding an enantiomerically enriched tartrate derivative. The oxidant for the epoxidation is tertiary butyl hydroperoxide. The reaction is catalyzed by titanium tetra isopropoxide, which binds the hydroperoxide, the allylic alcohol group, and the asymmetric tartrate ligand via oxygen atoms. Jacobsen epoxidation. Jacobsen epoxidation is complementary to the Sharpless epoxidation. Compared to the Sharpless epoxidation, the Jacobsen epoxidation allows a broader substrate scope for the transformation. Good substrates are conjugated cis-olefins or alkyl-substituted cis-olefins bearing one bulky alkyl group. The Jacobsen epoxidation gains its stereoselectivity from a C2 symmetric manganese 3-salin-like ligand, which is used in catalytic amounts. The manganese atom transfers an oxygen atom from chlorine bleach, or a similar oxidant. Epoxy characterization. Spectroscopic techniques such as Fourier transform infrared spectroscopy and nuclear magnetic resonance (NMR) spectroscopy are used to understand chemical structural features of epoxies, such as the presence of functional groups and chemical linkages. For example, the important bands corresponding to the oxyrane rings, hydroxyl groups, and ether linkages of DGEBA are observed in the Fourier transform infrared spectrum at around 915, 3400, and 1250 centimeter inverse, respectively. Similarly, the chemical shift values at about delta equals 3.3 parts per million, 1H, oxyrane, and 2.7 and 2.8 parts per million, 2H, oxyrane, in the 1H NMR spectrum, and delta equals 43 parts per million, CH2 oxyrane, and 49 parts per million, CH oxyrane, in the 13 CNMR spectrum of the epoxy confirmed the presence of an oxyrane ring. The epoxy equivalent weight, EEW, which refers to the amount of epoxy in grams containing one equivalent of epoxide groups, is estimated by refluxing a known amount of epoxy with an excess amount of HCl or HBr solution using pyridine as the catalyst, and then titrating the unused free acid against a standard NaOH or KOH solution using phenolphthalein as the indicator. Thus, the epoxy equivalent is the exact weight of the epoxy used divided by the difference in volumes of standard alkali required for the blank without epoxy and for the epoxy solution, multiplied by 1,000 times the normality of the alkali solution. Similarly, the hydroxyl value is defined as the amount of KOH in milligrams required to neutralize the free acetic acid obtained after binding 1 gram of epoxy containing free hydroxyl groups, which is estimated by acetylating the epoxy with an excess amount of acetic anhydride in the presence of pyridine catalyst in accordance with the standard ASTME 222-10 method. Once epoxies are synthesized, purified, and characterized, it is used to generate the epoxy thermosets. Thermosetting epoxies are cured to form three-dimensional network structures with high-dimensional stability. The curing time of an epoxy depends on its epoxy equivalent, the epoxy to hardener ratio, the number of active protons and reactivity of the curing agent, and environmental conditions such as the temperature of curing.